Hey guys, welcome to today's presentation. Hope you guys all had a great Christmas break. I hope it was safe. I hope it was fun. I hope you guys got to relax, got to turn off your physical science brains there for a couple weeks, and enjoy time with family and everyone um, over that holiday break. So, welcome back. It is time to get back to work. Couple of reminders: we are down to the last 2 weeks of the semester. If you have late work, I'm saying that late work, and I'll write this down here. Maybe. Hold on, my Apple Pen connected. Okay, let's say late work due by Friday. Okay, so late work is going to be due by Friday. If you turn in late work to me on Monday, I'm not going to accept it. It'll stay as a 0 in the grade book. So as this week kind of chugs along, it might be a good time to review your Schoology, see what's missing, and then try to get anything that's missing into me as we move towards the end of the semester, and look towards quarter number 3. Okay, it is I'm calling it the second half of the year now. Even though we still have these 2 weeks left, I always kind of view once a post Christmas break life. I view post Christmas break life as the second half of the year, moving towards spring break, moving towards summer. So you guys know what the expectations are in this class. The expectations aren't going to change. You guys did a great job first semester, and so far closing this next 2 weeks out, and I expect you guys to continue to do a good job. So if you are at home, all materials for this week's playlist are on Schoology. So if you're part of the Gold group, feel free to start your playlist with the materials that are posted on Schoology. If you are part of the Blue group, okay, you should be able to pick up everything you need for your playlist hard copy by the time you leave school on, I think your last day is Tuesday this week, if I'm correct. I have to check that for sure though. But your last day of school, the last day you're here, okay, you will be able to pick up all of your playlist materials. Okay, so if you have questions about that, please let me know. Okay, so this week we are going to start talking about mechanical waves and different types of waves. It's more of like an intro to waves section or unit this week. We are going to try to squeeze in like a big quiz mini test at the end of next week before we go on that long weekend, which is, I think, MLK Day. It was on that Monday. I think you guys are off next Friday. I have to check that and make sure. But we're going to try to squeeze in a big quiz mini test, possibly somewhere in that time frame. If we don't get to it, I'll push it to after this quarter. That test won't count towards this quarter. But everything on this playlist is going to be your last grade, okay, for the quarter. Everything we do next week is just going to go towards third quarter, okay? So just so you guys have an idea of what's due grade wise. All right. So waves for our warm up. Go ahead and pause the video. Try to write something down here, but you skip a smooth pebble across the river on a gorgeous sunny day. What does the water look like as the pebble skips across the water? Pause the video, kind of give yourself, you can draw a picture. I don't really care what you do. You can write words, but just kind of answer that question to kind of give us a visual representation of what we're talking about to start the unit. So pause the video and give yourself a second to do that. Okay, so some of the things that you might have mentioned are, as this pebble, if this is my pebble, as it's skipping across the water, we're going to have these rings that are starting to go out in all directions that come from the pebble hitting the water, right? And that's kind of like how we can think of waves, okay? Waves are always going to come from some sort of source, all right? When that pebble hits the water, that's creating the ripple or the wave that you're seeing on the river, and that wave propagates out from that source, right? It goes in all directions from where that pebble hit the water. And that's how our waves are going to work too. Okay, every wave is going to have a source, and wherever that source is, it's going to propagate in all directions from that source, okay, in the form of waves. Okay, so let's go ahead and look at our I can statements for this unit. I can, number one, I can explain how waves interfere with one another through constructive and destructive interference. Okay, that's reflection, that's refraction. Okay, and we'll give you guys definitions of that. You're probably familiar with reflection, maybe a little less familiar with refraction. Okay. Number two, I can show how the properties of a wave depend on the material. Okay, I can explain the behavior of waves in different media in terms of absorption, reflection, refraction, and diffraction. Okay, so that's similar to what we just talked about, reflection, refraction. I can identify basic sources of radiant energy: light, X-ray, gamma ray, micro, infrared, and radio. I can create or provide an example of a situation that one person would experience the Doppler effect. And I can correctly utilize the terminology for this unit. Okay, so first term we are going to talk about are waves. I'm sure you guys can pause the video here, write down what you think of as a wave. Wave has other meanings. I'm sure many of you guys think of like waves on the ocean, okay, or something along those lines. Waves in science mean something a little bit different, okay, but the general idea of it is the same, I would say. Okay, so a wave is a form of energy okay, so waves are a form of energy. That can travel through different media. Okay, so some of you are probably thinking, Mr. Murphy, what is this word media? What does that mean? Okay, so what we are really saying is that waves are a form of energy. Okay, so when you think of something like a microwave, okay, microwaves can be produced by your microwave at home. Okay, radio waves can be produced by like a radio tower. Okay, so those are all forms of energy. Okay, and when we say they can travel through different media, we're saying that they can travel through different materials or substances. Okay, so your radio waves might travel through the air, all right? But light waves can travel through water, okay? That's why you can see the bottom of a pool. Or if you're at a lake over the summer or in the river over the summer, you can see your toes sometimes if the water's really clear on a good day. Okay, that's because light is traveling through the air. It can also travel through the water, okay? So waves are a form of energy that can travel through different media. Okay? Like we just said, waves are forms of energy. Waves are a form of energy, and there's many types of waves, all right? Some examples are, and you've already heard me reference a couple, radio waves, microwaves, light. Okay, light is a wave. All right. All of these are different types of energy that are all traveling in different forms and different wavelengths and have their own specific properties. Okay, so the third bullet point here asks you, are all waves visible? Okay, are all waves visible? Okay, and the answer to this question is, of course, no. Think about that. Okay, when you're in your car on the way to school, okay, and you flip on 94.1 and start bumping to some country music, okay, can you see the waves traveling to your car? Absolutely not. Okay, when you go home at night, okay, after a good basketball practice or cheer practice, can you see the microwaves that are heating up your food in the microwave? No, you can't, okay? So not all waves are visible, but some are, okay? You can see visible light, right? Okay, and there's different forms of visible light, okay? There's red light, there's violet, okay? And we'll kind of get into that a little bit more next week when we get into more of the electromagnetic spectrum and what that is, okay? But some forms of waves, okay, are visible. Okay, so characteristics of waves. This unit this week is a little vocabulary heavy. There's not much math in this week. Okay, so that's something that some of us probably will enjoy. Some of us probably aren't huge math people. I know I'm not a huge math person at times, but it is pretty heavy on the vocab. So I think it's important to get clear definitions for all of this stuff down in your notes. That way we're all on the same page. Okay, so you'll hear me reference this type of stuff throughout the week, this week, and next week. So frequency is our first definition. Okay, frequency is the number of waves, okay, the number of waves that pass a fixed point in a given unit of time. Okay, so the number of waves that pass through a fixed point in a given unit of time, and the unit for that is hertz, okay? We will use the abbreviation HZ to refer to hertz, okay? If I move through these definitions too fast, pause the video, get it down, resume the video for the next definition, okay? That's kind of the advantage of having a video is I can move at a good pace for me, where I'm not waiting for you guys to continue to write the whole time, and then you guys can kind of pause it, go back, look at what I say, and then revisit it as many times as you need to. Okay, so the next definition, and I'm going to kind of switch colors here to kind of keep it divided, is amplitude. Okay, amplitude is the maximum displacement or distance that a wave is displaced from the normal. Okay, and some of these are more easily understood with a picture, and we have a picture we're going to label here in about 2 slides once we get all these definitions down. Okay. The next one is a trough. Okay, you might be familiar with what a trough is. Okay, so a trough for a wave is the lowest point a wave is displaced from the normal. Okay, this is slightly different, obviously, than the crest, which would be the exact opposite, which is the highest point. A wave is displaced from the normal. Okay, wavelength, which we are going to be hearing a lot about. Okay, wavelength is the distance from crest to crest or trough to trough in a wave. Okay, and wavelength is usually measured in meters. Okay. There are two general type of waves. One is a longitudinal wave. One is a transverse wave. Okay, a longitudinal wave, all right, is the first one we're going to talk about here, and it is a wave that vibrates in direction or parallel to propagation. Okay, so pause the video, get that definition down, but I'm going to continue talking about longitudinal waves for a second. So longitudinal waves, some of us might be confused with what the word propagation means, and I kind of made the transverse wave definition a little bit easier for you, but all a longitudinal wave is it's a wave that when it's moving, guys, when it's vibrating, it's going in the direction of what, like, the movement of the wave is, okay? The transverse wave is a little bit different, okay? Transverse waves are waves in which motion occurs at right angles. Okay, which motion occurs at right angles to the direction of the wave. Grab a different color here. Okay, so the big difference, guys, is the direction they're going. We said this one is going in direction, okay, or parallel. All right, transverse waves are at right angles to the direction of the wave, okay? So one's going with the direction, okay, and one's going opposing the direction, okay, or at a right angle. All right, so now we're going to label a couple things on this picture here. All right, one thing I didn't put up here in the description, I do want to label the amplitude as well, so we're going to add that in there as well. Okay, so here, our first thing we're going to label is our crest. Okay, there are multiple crests here, obviously. This is one of them, crest. Okay, this is also a crest, crest, crest. All right, so crest is just the maximum height of that wave. Next thing we're going to look at is the trough. Okay, trough is just the opposite. Our definition for wavelength is the distance from peak to peak or from trough to trough. Okay, so wavelength is, if we call this a crest to crest, all right, wavelength would be that distance right there. All right, wavelength can be seen multiple times, okay? That's another example of wavelength. Okay, so when we're looking at these guys, there's not just one crest. There's not just one trough, okay? There's not just one wavelength. Wavelength is any of these measurements, okay? Notice that this distance up here, all right, x. All right, we'll call that distance x. All right, it's the same distance throughout. It's not changing over the course of this wave. The wavelength stays the same, okay? And like I said, we're going to add one more here, which is amplitude. All right, amplitude is any of these distances right here. It's how much our wave is displaced from the normal line, or this line right here. That's what we're calling the normal, okay? So amplitude is any distance that we are displaced from that normal line, okay? Crest, trough, wavelength, amplitude, okay? You will be asked to label a picture like this on your big quiz / mini test on waves at the end of next week or early the week after that, okay? So just keep that in mind. This picture is important. I think it's easier to visually see what some of this stuff means rather than the formal definition. I know the formal definition can get kind of wordy. Okay, so wavelength and frequency. All right, we said wavelength, if you look up here, all right, is that distance from peak to peak, or I'm sorry, crest to crest, or trough to trough, okay? Frequency is how many waves we are seeing in a given amount of time. So the relationship between wavelength and frequency is inverse, okay? And what does that mean? Okay, inverse means that the bigger the wavelength, the lower the frequency. It also means that the smaller the wavelength, the higher the frequency. Okay, so representing this visually, and what do I mean by this? First, I want to create a bigger wavelength. So let's create a big wavelength. All right. There is our distance from peak to peak, roughly. All right, so that is a big wavelength. All right, that means there's going to be less waves in a given amount of time. All right, so you can see here that my line is much longer, which means that I'm not going to see as many waves in a short amount of time. Okay, let's draw basically the opposite picture and see what it looks like. Okay, for something that has a smaller wavelength, would look something like this. Okay, here is the distance from peak to peak now. It's smaller, but I see more waves on my line. I am getting more waves in a given amount of time, okay? So the bigger the wavelength, the lower the frequency, the less amount of waves I'm seeing in a certain amount of time. The smaller the wavelength, the higher the frequency, the more waves I'm seeing in a given amount of time, okay? Now we're going to move into refraction and reflection. Okay, refraction, all right, is a change in direction of waves as they pass from one medium to another. Okay, that's also referred to as like bending, all right? So change in direction of waves as they pass from one medium to another medium, okay, or bending of the wave. Okay, the next definition is reflection. Reflection is exactly what you would think reflection to be, okay? All waves can either refract or reflect, okay? They can do both simultaneously, okay? So you can get something that a material that's going to reflect some of the wave and refract some of the wave simultaneously. Okay, so you can get some of that simultaneously. Reflection of the wave involves a change in direction. Involves a change in direction as they bounce off a barrier. Okay, so reflection. All right, an example of this is in the summertime. Picture yourself at the pool. Okay, here's you at the pool, and I'm sure back when you were a kid, you used to throw like those diving sticks or diving toys down here at the bottom of the pool. Okay, so let's call that the actual resting point of the diving stick. All right, what you may not know is that what you are seeing from the surface up here where you stand is not where the diving stick actually is at the bottom of the pool. Okay, the reason that is because as light, and we'll represent this in yellow, as light is coming down to the surface of the water, all right, it begins to bend in direction. Okay, so the light isn't traveling the same direction that it was earlier. Okay, this skews or this messes up what you're actually seeing. Okay, so this is refraction of the light. Okay, it's bending, so it's moving what you're seeing at the bottom of the pool. Okay, rather than seeing the diving toy where it actually is, this might be its actual position. Okay, this is what you're seeing up top, and that's the refracted position. Okay, and that's a little bit different than where it actually is being seen by you. Okay, so you're not actually seeing it when you're standing up top and you're looking down into the water at a diving stick. You're not actually seeing where the diving stick's at. You're seeing a refracted picture of where the diving stick's at. Now, the reality is that light bends so little in water, it's pretty close. And then once you dive into the water, your eyes adjust regularly to the refracted or the bended light, so you're easily able to locate the diving stick. Okay, so that's kind of an example for you there. All right, last slide, we're going to talk about this thing called the Doppler effect. Okay, a Doppler effect is an increase, an increase or decrease, increase or decrease in frequency. Okay, and you can think of frequency in this case as like the loudness, okay, of sound, light, or other waves. As the source moves toward or away from you. Okay, and this is something that you're probably familiar with. It's something that happens to you every day when you're driving. Well, I guess you guys probably don't all drive, but when you theoretically are in the car with your mom or your dad or whoever it is that you're with at that time, a friend, okay, and you hear police sirens or ambulance sirens in the background. All right, it starts off not as loud as it's further away from you. As that car approaches you, okay, as the car approaches you, the sound begins to get louder, all right? As the car is just passing you, the sound is loudest, right? And then as the police car whizzes by you and it's going to pull somebody else over, because we all know you guys never speed, or will never speed when you guys drive, okay? It begins to get less loud as the police car moves away, okay? So that's the Doppler effect, just kind of the source of the wave, okay? Whether it's a light wave, microwave, radio wave, matters, okay? The Doppler effect is why if you are listening to the radio and let's say you're going on vacation to Florida and you're driving there, okay, the radio station starts to go out the further away you get. That's part of the Doppler effect, right? Because you're getting farther away from the source of that wave, okay? So the Doppler effect is basically just this idea that the source of the wave does matter. It does play into some effect of how we see or view that wave, okay? So that's going to kind of wrap up our presentation for today. Like I said, feel free to pause this video throughout. Take any notes that you might need. The importance today is kind of our Mondays are always our note-taking day. It's our heavy lifting day for the week. And then Tuesday, Wednesday, Thursday is going to be our typical playlist days. Playlist due Friday, checkpoint Friday, as we kind of wrap up the week. I do have a small group activity that I'm going to be doing with you guys. I will do that with you when you are in school for Online Warriors. You'll kind of have to do the activity on your own, which kind of just is what it is, I guess. But if you guys have any questions, feel free to pause the video, hop on Zoom. The doorbell's turned on Zoom so I can hear. It gives me the ding-ding when you guys enter the lobby, so I can go up there, admit you, and help you out if you're having any issues, okay? So appreciate you guys watching the video. If you guys have any questions, feel free to reach out to me with questions. Obviously, I want to help you guys as much as I can here. So thank you. Have a great day, and look forward to having a good first week back here.